Morning. How are you? Good. Any questions on the previous lectures, homeworks, assignments of any kind? We need to prepare more questions. I love questions. All right, so last time we talked about non-minimal systems, and non-minimal systems are such systems. I think we have some sort of echo here. No. Okay. So we talked about non-minimal systems, which are not controllable or not observable or both. So in that kind of case, we need to handle them a little bit differently. For them, we are defining stabilizability and detectability. And this means that if system is stabilizable, you still can design controller for that system to deliver your poles, but not all of your poles wherever you need it. Some of the poles. And if the rest of the poles are stable, that's still okay. You can still design your controller. It will not just converge the way you want it to converge ideally. Now, detectable system means that you can design observer, but you cannot decide on how fast it would converge. This is the problem of all of the systems. So today we will be solving problems related to stabilizability and detectability, and we will try to design controllers and observers to that type of systems which are non-minimal, which means you have cancellations of zeros and poles, and these systems are pretty actually typical in physics and other places, so it's not like very unusual to see that type of system, and we still want to control it somehow. Also, if you'll have enough time, I want to start working on MATLAB implementations of all the things that we learned so far, which means all of the linear algebra, controller design, observer design, other things, how you do that in MATLAB. And it's pretty simple. Practically every single thing that we need to do, it's 1 or 2 lines of MATLAB code. So it's very simple, relatively, compared to what you used to see maybe in Controls 1. I will show maybe also a few ways to do the same thing, because, for example, you can work with symbolic polynomials, where you have like s squared plus something, s plus something, right? So you can have that s squared, or you can represent that as just vector of coefficients, which is just regular vector in MATLAB, right? So you can, they're equivalent representations of the polynomial, but some representations are easier for something specific, and some other representations might be more convenient for something else. So we will talk about both ways to represent polynomials, computing multiple ways, computing controllers, and things of that kind. So this will be the topic for today. All right. Any questions? Okay, so first question that we will be solving today is theoretical question. And this question, I promised that last time to show you some system which has zero transfer function, which is very interesting system. An unusual system. Why? Because all of the vectors that we will be having in that system, representation of the system, are not zero. So you might have state space representation, which is giving you zero transfer function, but it is not zero representation, okay? It's like not matrices of zeros, because otherwise it will be trivial, right? Obviously b equals to 0 or c equals to 0, obviously b times si minus a inverse times c equals to 0, right? Because one of the vectors is 0, so 0 multiplied by anything is 0, so it's not that interesting. But I'm saying we will find such a vector that is not 0, and transfer function still will be 0. Okay, so here's the question. You have seesaw system with matrices A, B, C, assuming d equals to 0, and A, B is not controllable pair. So some not controllable pair, which means controllability matrix of A and B, it's having rank less than n. This is all we know about the system, and I'm not giving you any other details on the system. This is just generic non-controllable system, okay? We need to prove mathematically that such C vector exists, which is not equal to 0, that the transfer function is 0. This is a problem that we are going to solve. Is it clear what we are planning to do? So you have some generic system, whatever it is, the only knowledge that you have about the system is that this system is not controllable. So you have some cancellation of zero and pole, and this cancellation is not controllable. It could be stable, unstable, whatever, right? I am claiming that I can find such a C, which is not zero, and the system has transfer function of zero, and B is also it's not zero, right? And I will find that kind of system, right? So here's how we do that. So we have all these matrices A, B, C, and without breaking any generality, I will assume that they are in canonical non-controllable state. Why is that? Why is that not breaking any generality? Without losing any generality, I can claim that they are given in the form of not controllable system, canonical system. If you remember, canonical system was of the kind you had like A1, A2 block, A 3 block, and 0 block. This was my A. B was some B1, B2 blocks. Each one of them is block of the appropriate rank size, okay? So it depends on what R is, which is rank of the controllability matrix. This will be R by R matrix. This will be N minus R by N minus R matrix, block, and so on. Remember that part? Okay. And matrix C will have that kind of shape, which is C block and 0 block. So my claim is that I will find such C1 which is not 0, but transfer function of that entire thing will be 0. Okay, this is the claim. Okay, so far. So this is a problem that we are trying to solve. But the question is, why I'm not breaking any generality here? So I'm saying like, I can assume that this is my representation of the system. And why is it generic? What do you think? This is obviously not all possible non-controllable systems, right? You might have non-controllable system represented in a different way. So why I'm saying if I'm proving that for that system, then it's true for any non-controllable system. Yeah, let's try a more generic question, even more general question. If I prove any property for transfer function of that system, why this would be also true for any non-controllable system? So what happens to transfer functions of any non-controllable system and this system which represents the same system? It's different states, obviously. So what is the relation? The systems are similar. What is the relation? Similar in mathematical sense, not similar in the general language. Similar means that you can transform from one to another. Okay, so what do you know about similar systems? They have same eigenvalues, same transfer function, practically same system in terms of controls, right? They might have different initial conditions. This is what could be different. But other than that, they are the same system, same differential equation, and so on. Okay, so if I prove something for that system, that transform from that system back to the C, which is the original C, is just multiplied by matrix T, the transform matrix. Remember, this is TC. This is the transform. So you need to invert that matrix, and this matrix is invertible transform matrix, right? So it just will multiply that by matrix T, and still will be not zero. Okay, so some given invertible matrix. And all other properties will be the same way. So if I prove anything for that system, I have similarity transform to any other system backwards, get your original system somehow. And I can transform all of these properties. But the transfer function of that system is exactly the same transfer function as of your original system, which is also zero, obviously, if this transfer function is zero. Right? You get the same transfer function for all the representations. And we know now that any non-controllable system could be converted into that thing. And we even proposed particular transform which is doing that. Okay, so putting our first columns of the controllability matrix, and then you complementing that with additional independent columns. Okay, this is how you get the transform. So you know the actual transform which would do that, right? So it's always possible. If it is always possible, transfer function is zero for that one means that every single representation of the same system will have transfer function of zero because they all similar, have the same properties. All right, so let's see why transfer function of that thing could be zero. Okay, so let's see how it goes. Okay, so for transfer function, all we need to do is to compute the actual g of s. And we have formula for that, which will be c times si minus a inverse times b. Okay. Okay. Oops. This was incorrect what I wrote here. This should be zero for control. This one, C2. This one is zero. Sorry about that. Pay attention. The second half of B is zero, not the second half of C. This is second half of C is zero only when it is not observable. Okay. All right, so I'm just copying all of the things here. So it's like C1 log C2 times Si minus A, which would be also some sort of log Si minus A1 here, Si minus A3 here, minus A2, log of zeros. Okay, inverse A1 block and zero block. I'm just copying these definitions into the regular formula transfer function. All right. Now, very conveniently, this is block triangular matrix. Right? So you have block of zeros, which means that inversion of that matrix, you have formula for that. You inverting that part, and you have some formula for inverting that part. Okay. So let's see what you get here. I'm just using that formula. I'm copying C1, C2. Then you have pretty big matrix. Give it some space. We do not have much space here. So it's inverting that matrix as I minus A1 inverse. Here we will have that element that I will write at the top here. Here I will have Si minus A3 inverse. And here I will have block of zeros. Okay. Here I will have B1, 0. Okay, so this element would be something like that. It's practically that element times that element times that element. So all of them together. It's like this one inverse, this inverse, and in the middle you have that element. So it would be something like that. It would be Si minus A1 inverse, A2 and plus I minus A 3 inverse. Something like that. This is that thing. Question so far? Okay, now let's try to simplify it and to multiply that matrix by that vector, block by block. Okay, so it's this one times B1, this one times 0, and then you have 0 times this thing, this one times 0, right? That will be pretty simple. You see why most of the things are canceling? Why I don't even really need to write that part? Because it will be multiplied by 0 here. These are blocks, right? Okay, so this is what we get. We still have C1 block C2 times matrix, which is as I minus A1 inverse B1 block of 0. And practically that's it. Right? So now we multiplying Z block by Z block. So you get C1 times that thing plus C2 times 0. So you get C1 as I minus A1 inverse B1. Now, what is the last step that I need to do? So this is transfer function of that particular system. Do they want to go? That C, which is not 0, exists, that this thing will be 0 something. Okay. So what should I do? What is my C? Which is not 0. But transfer function is 0 for any other matrices.
And on 0 is 2.
That's it. And this is clearly not 0, right? These values are not 0. There are some even values. You just start the matrix, see these zeros, block of R zeros, and then some other numbers. So this is C1. C1, just you pick this one, equal to 0. Then that entire thing is obviously 0. If you pick matrix C like that, the transfer function always will be 0, regardless of what other matrices or values are. Okay? So we have proven that you can always pick such values like that for that system, which means that you can do transform of that matrix to any other non-controllable system representation, and you'll get transfer function of 0, which is interesting because typically you do not meet that type of systems. It multiplies by 0 practically every single signal you have. That's only transient responses and nothing else. Transfer function is completely 0. Multiplies by 0 every single frequency. Big blank circuit. All right. Any questions? Okay. So now we have another more technical exercise, which is talking about stabilizability, detectability, controllability, observability, designing controllers. And I will give you just example. I will not really get into technical computation of multiplications of all of these matrices. You can check that in MATLAB or by hand, whatever you prefer. The example is like 3 by 3 matrices, just for fun. That will be more space on the board. And the question is that you have some system given to you, some particular system, Let me move to another board here. Just checking that the camera is recording particular place. Okay. These cameras are tricky. All right. So you have the following system. You have x dot equals x plus bu, y equals cx, and matrices are given as follows. So matrix A is 1, 0, 0, 0, minus 1, 0, minus 2, 2, 1. Matrix B is 1, 0, 1. Matrix C is 1, 0, 0. Okay, this is a system. Okay, given system. Part A is to check controllability and observability of the system, just to make sure that it's not controllable, not observable, because this is the topic, right? So part 1, check observability, controllability. Okay. How do we do that? We find controllability matrix and observability matrix. So here is your controllability matrix, which would be first vector B, which is 1, 0, 1. Then you need to multiply this one by this one, so it will be again 1, 0, and minus 2 plus 1 will be 1. Okay. And then you need to multiply matrix A by Z vector. So it's 1 times 1 will be 1. Okay. 0 minus 1, 1 multiplied by Z vector will be still 0. And minus 2 minus 1 will be minus 3. Okay, so I'm just multiplying matrix A by Z vector. I'm getting the third vector, which would be A squared B. Clear so far what I'm doing here? I'm just computing controllability matrix. So this is vector B, this is AB, this is A squared B. That's all you have. But I don't need to square it, I don't need to compute like A squared, because A squared B is A multiplied by AB. So it's that vector. And you can always do that. Like you're taking A multiplied by the previous vector, we can use the next vector. Okay? So obviously this is not full rank because you have 0 line here. So what is that rank? How many dependent columns or rows you have? So this is definitely dependent on A. So it's definitely not 3, but do you have 2 independent vectors here, at least? You do have them. So this vector is independent of that vector, because this vector is not proportional to this vector. So rank is 2. The system is not controllable for all these reasons. Okay, and you have 1 non-controllable pole. That's what it means, right? Rank 2 means that you are missing 1 to get 3. So 1 uncontrollable. Okay, observability. So I'm copying the C matrix, which is 1, 0, 0. Then I need to multiply A, and then you will get CA. So 1 times that one will be 1, times the second one it will be 0, times the third one it will be 0. Right? I'm just multiplying C by A. So it's like this one by this one, this one by this one. No, not by this one. This one by this one, this one by this one. right? Yeah, you get first. Just multiplication. And third line will be, again, I'm taking exactly the same thing. So what should be the result? Should be the same. So you get exactly the same vector. Okay. So what do we see here about rank of observability matrix? How many independent rows or columns you have? So both of these are dependent. You left only with one. Okay. So this one is one, which means you have two not observable ones. Okay, so you have one not controllable one and two non-observable ones. All right. What does it mean in terms of poles which are not observable and not controllable? Combinatorially. So you have one which is not observable and not controllable. So you have total three. Okay, if two of them are not controllable and one of them not observable, that would cancel the entire thing. All of them would be different. Okay, so you have some overlap in a sense. All right, but it's a side question. You don't really care about that combinatorial part here. It's just comment. All right. Okay, so this is part number one. Part number two, check stabilizability and detectability of the system. So this is part two. If the system is stabilizable and if the system is detectable. What do we need to do for that? What do we need to know? What is stabilizable? That's previous lecture. What do you mean by stabilizable? What are the properties of stabilizable system? It's not controllable. I mean, we know it's not controllable. The rank is lower than 3, so it's not controllable. Stabilizable means that all of the non-controllable poles are stable. But you need to know them first, right? So you need to find eigenvalues of the system first to identify them if they're controllable or not controllable. And then you can say if they're stable, then the system is stabilizable. But if not, then the system is not stabilizable. Okay, so how do you know eigenvalues of that matrix? What are eigenvalues of that matrix? Eigenvalues, yeah. Exactly, why? This is triangular matrix. For triangular matrices, all the eigenvalues sitting on the main diagonal. So that's simple. You can divide it also into blocks and to use it in different ways. Whatever the way you choose, you can, by the way, you can divide it in that type of block, let's say like that. Or you can divide it like that. You can divide it in multiple different ways. And then you'll have block of zeros here or block of zeros there. You'll be block triangle. You can divide it in any way which is convenient to you. But in that case, this matrix is very simple. So your eigenvalues are just sitting on the main diagonal. Okay. So you clearly have one stable eigenvalue and two unstable ones. All right. So now you need to identify if the system is stabilizable, which means it will be stabilizable. And this rank is 2, which means that you need to figure out one which was canceled and not stable or stable, right? So this could be any of them. How do you know which one is which? How do you know which one of them is what was cancelled and stabilized or stable or not stable? Which one was related to the deficiency in rank? Sorry? Sign? Sign of what? Okay, so the direct way is to find transform to canonical non-controllable state. And then all of your controllable poles will jump into the upper left corner, and non-controllable will jump into the right bottom corner of the matrix A after the transform. So this is classical way which works always for any kind of matrices. But in that case, you don't even need to do that, really. Can you see that just from the matrix, which one is not controllable? Based on the hints that we discussed previous time. Like, look at the actual equations, how the equations look like. So for being not controllable, it needs to be dependent on itself and not on input. So you cannot control it, right? So pay attention to that equation. So I have x2 dot is minus x2, and that's it. No relation to you, no relation to other x's. It relates to itself. It will just go and decay to zero based on the exponent of minus t. That's it. You cannot control it. You cannot do anything. But it is stable because this is minus one. Okay, so the system is stabilizable. You can stabilize the system, right? Now, so just to write that down, x2 dot equals minus x2. It's stable. This eigenvalue is minus one here, right? So it's stabilizable. What about detectability? Again, classical way to convert it into canonical state of non-observable state, non-observable form. Right, this is a classical way to do it. You're finding transform, you're computing all this similarity transforms, and you convert it, and you'll have all of the observable eigenvalues sitting at the top left and non-observable at the bottom right in your transform matrix. But do you really need to do that here? The answer is no. Why not? So what is detectability? Detectability means that all of the non-observable poles, which were cancelled, obviously, are stable. How many of them were not observable? 2, because the rank is 1. The rank of matrix of observability is 1, which means 2 were not observable. Pick 2 stable ones. Can you? Pick any stable ones. You need 2, which will be stable, and then the system will be detectable if you can. Potentially, I mean, but you can't. The thing is that you have 2 unstable here, right? So no matter what pair you choose, at least one of them will be unstable. No matter which pair you choose, like -1 and 1, -1 and 1, 1 and 1. These are the pairs that you have, right? So you need to choose 2 which will be stable. You can't. You have only 1 stable. So no matter what you choose, and no matter in which order, which one of them are not observable, at least one of them will be also unstable. Combinatorially, again, just from combinatorics assumption, okay? So the system is not detectable. No matter what you do, one of them will be unstable. So since 2 poles stable. And two poles are not observable. You know that the system is not detectable. All right. Now let's do the same thing with the actual transform. I just want to show you for the first one how you get to the same conclusion based on the transform. Again, I'm not really computing all this matrix. I will show you just the solution to see that you get exactly the same thing. So the transform that we need to do is the following transform. This transform will be, if you remember, rank is 2, which means that you need 2 columns from the controllability matrix, right? So what are the 2 columns of the controllability matrix? Is 1, 0, 1, and then 1, 0, minus 1. Now you need to complement that with additional vector, which is independent of these 2 vectors. So what? Can you propose some vector? Something simple, which will be completely independent of these 2. So you definitely don't want 0 here, right? Because otherwise this will be like line of zeros. This is not invertible matrix. So let's pick just 1 here. Or you can pick any other number, whatever. The thing is that this should not be vector of zeros here. Otherwise, you cannot invert it. But you can compute determinant of that and see that this matrix is invertible. Everything is fine. All the vectors are independent. And then you're computing a transformed would be T inverse AT. And the matrix that you get is 0, minus 1, 2 block, 0, 0 block, then 1, negative 1, negative 1. You can think about that as that type of blocks. So you need block R by R, which is 2 by 2, and then block which is 1 by 1. So this is the non-controllable part. So eigenvalues of that matrix, which are the value itself, is not controllable. Eigenvalues of that matrix are controllable, and they will be what? What will be the eigenvalues of that matrix? You don't need even to compute that. I mean, you can. That of Si minus that thing and find roots of that polynomial, but you don't need to. You know what's the eigenvalues here from your original matrix. Remember, eigenvalues are exactly the same like in the original system. So you have minus 1 and 1 and 1. So you have 2 eigenvalues of 1, which are eigenvalues of that block. Okay, that's it. So from that, you know that this value is controllable, not controllable, but stable. So the system is stabilizable. Practically, that's all you need to know about that. And I'm not really inverting that matrix here. Okay, any questions on that? All right. So if the system is stabilizable, let's try to design controller for it. Closed loop controller, and we have particular requirements for that controller. So we want to stabilize it with state feedback. And by the way, obviously you cannot design observer to that system because system is not detectable. So you cannot do anything with observer. So you need to measure all of the states to make it work. Let me move to the board. All right, so how we design the controller for that thing? We definitely need to decide first on where the poles need to be. But technically, it doesn't matter that much. Like you can design them in particular places. I will show you only one thing that you need to be very careful about. when you're designing your location of poles, at least one of them needs to be there. Okay, so what we are doing, we are comparing alpha s with a k of s. Let's say comparison of coefficients for the two polynomials, right? So this would be always s minus 1. That's actually plus 1. It's negative 1. S minus minus 1, right? Times, I don't know, let's pick some values, s plus 3, s plus 5. Okay, you choose your location at minus 1, minus 5, minus 3. All right, some location. So you pick that thing, and here you have determinant si minus a plus bk. So what you get here is determinant and a lot of space. S minus 1, 0, 0, 0, S plus 1, 0, 2, minus 2, S minus 1. Plus matrix of K1, K2, K3. This is BK part, 0, 0, 0, and K1, K2, K3. Something like that. So when you do half an hour of algebra and you actually computing the determinant, I mean, you have a lot of zeros here, so it's not that big of a deal. You're just developing it by the second row, because this thing plus this thing will give you only s plus 1 in the middle, right? So you can develop by the second row, you will have determinant of 2 by 2 times that thing, right? So let's actually do that. So this will be determinant for, right, directed that thing. It will be determinant of s minus 1 plus k1. Right, second element will be k2. Third element will be k3. And here you'll have 0, s plus 1, and 0. And third one will be 2 plus k1, minus 2 plus k2, and s minus 1 plus k3. Right, this is a determinant. So we are developing the determinant by the second column, which will make it s plus 1 times determinant of these elements. Remember how you compute determinants? You're just crossing that column and that row and computing determinant of everything else, and multiplying by that thing times the minus 1 to the sum of its indices. And in that case, it will be even number, so it will be plus 1. Okay, this is minor computation of the determinant. So it will be the big thing, s minus 1 plus k1 times s minus 1 plus k3 minus k3 times 2 plus k1. That's it. Something like that. So the point is that this polynomial will always have that factor here, okay, that you cannot move. And it's not dependent on k. So no matter what k you're choosing here, okay, you will always have that kind of thing. So this needs to cancel with that part. So you always need to choose your desired pole wherever you have that not controllable pole, and then it will match. Because if you choose it like a plus 10, for example, it will not match. You'll not be able to design it. Okay, and in that case, you're just canceling these two, and then you're comparing coefficients of that quadratic polynomial to that quadratic polynomial. And then you're finding k1, k2, and k3, and that's it. Okay. practically done. Any questions? All right, so let's start working on MATLAB part, if you do not have any other questions related to that topic. Next time, hopefully we'll get finally to nonlinear systems, which are kind of more interesting, but we will convert them into close to linear systems in a way, so it will not be that different from what we have done before. And I just want to share the MATLAB part. Let's see. Projector will be in minutes. Is that fast? Do you see anything, or I need to make it bigger? Good enough. Okay, big enough. If you do not remember MATLAB, very basic things, how you define vectors, how you define matrices, how you compute all kinds of basic things. Let's see. To remove all of the other things which are on the way. It's better. Okay, so first of all, how you define column vector. So you are using semicolons between the numbers and then define that as column vector and not row vector. And you write in that way. It's a column vector. With commas or spaces, you can define row vectors, which would be that type of vectors, line vectors. This is how you do that. This is the type of vectors that you get. Okay, you just put commas between them. If you want matrices, you're doing the same thing. You define just vector and then semicolon. This is next line, another part. And then you can get like 4x3 matrix or any other shape of the matrix, depends on number of columns and rows you decided to use here, okay? So let's try that. Super convenient, but okay. Like half an hour to compute single vector, you see. Okay, so this is a matrix that you get. So you can see results on the right, okay? Here you see the actual result in the live script. I will publish the live script so you'll be able to see that. Okay. So how we compute determinant, trace, inverse, eigenvalues, all the linear algebra stuff that we talked about. Here's how you go. Huge delay here between. Okay. Let me maybe run all of them together. This would be much faster. So here's how it goes. So you have that matrix And I defined matrix like 1, 2, 3, first row, 4, 5, 6, second row, 0, 0, 1, third row. And I want to compute determinant. So determinant is just using function det of that matrix A. Gets you determinant of -3, which means that this matrix is invertible. All of the columns and rows are independent linearly. For trace, you're using function trace naturally, okay? And you get sum of all of the diagonal elements. This is what trace is. To inverse matrix, you have function inv, but you can just use power of -1. This works in MATLAB for matrices, okay? So if you want to invert matrix, you'll just get that kind of formula, and you will invert the matrix. This is how it will look like, right? The result is inverted matrix, inverse matrix. To compute eigenvalues, if you want only eigenvalues as a vector of numbers, which means you want just eigenvalue number 1, 2, 3, 4, 5, and so on, you're using single output, like EV or whatever name of the variable. So this EV will be a vector of 3 eigenvalues like that. They could be complex or real, depends on the matrix, obviously. But they will be a vector of numbers. But if you want that for example, diagonalization of the matrix, then you need to put them as diagonal matrix, right? You need to put them on the main diagonal. And you also want the transform of the eigenvectors, which would transform it into diagonal form. And this is how you get it. You're actually giving that eigen function 2 outputs. The first output will be eigenvectors, will be matrix of 3 eigenvectors in that case. So each column of that matrix will be eigenvector of the matrix. And second matrix will be diagonal matrix with the eigenvalues, corresponding eigenvalues on the main diagonal, okay? So this is how it will look like. Just to that. You see, you have all of the same eigenvalues from here that we have here, appearing here on the main diagonal. And here are the eigenvectors that you have, okay, for that thing. Any questions so far? All right. Just to test it, diagonalization transform, if you using the transform, which is eigenvectors times eigenvalues times eigenvectors inverse, which is similarity transform, you are obviously getting your matrix back, okay? And this will be the matrix. Remember, this is the original definition of matrix A. It's like 1, 2, 3, 4, 5, 6, 0, 0, 1. Space here. Okay, so this is the original matrix if you're doing that transform. Okay, polynomial roots. Again, I talked already about 2 different representations for polynomials. One is just vector of numbers, which would represent coefficients of the polynomial. And if you want some of the coefficients to disappear, you just put them 0, right? So if you want, for example, s squared plus 1, so you'll have it 1, 0, and 1, because nothing is multiplying s. So you will still need to pad it with zeros wherever you need it. Okay, is it clear what I'm saying? Like s squared plus 1 missing the s component. So you just multiplying it by 0. So these are the coefficients. So let's say this is the polynomial that you have. Polynomial is a simple vector. And if you want to find the roots of the polynomial using function roots of that polynomial, and it will give you all the complex or real roots like that. So these are the results of the roots of the polynomial. Obviously, order n polynomial will have n roots, always, complex or real. Any questions so far? Characteristic polynomial of given matrix. So you have matrix A, you want to find characteristic polynomial of that matrix A. You're using function characteristic poly, char poly, okay, of that matrix, and you get that polynomial as a vector of coefficients. Now, let's say you want it not as a vector of coefficients, but you want it in actual symbols with s squared, s cubed, or whatever, okay? So then you need to define variable s as a symbolic variable. And this is how you define it, using sims and s. this defines symbolic variable s. And then you can use that in determinants or any other functions that you want, okay? And obviously characteristic polynomial is determinant of si minus a. Function I, which is identity matrix, is actually written as E, like that, like I, you know, for whatever reason. So they call it I. And this is order of that matrix I. So it's 3 by 3 matrix because the dimensions need to match. Your A matrix was 3 by 3. So that I matrix also will be 3 by 3. So you're defining that as I of 3. So it's symbolical variable S times matrix I minus A, determinant of that. And this is what you will get. Okay, this is the polynomial. Obviously, exactly the same polynomial like here, right? These are exactly the same coefficients, which is like 1 coefficient minus 7 plus 3 and plus 3, right? Same thing here and there. These both are same, but this is kind of nicer representation, more algebraic representation, more symbolic representation. Sometimes it gets a little bit complicated. You have multiple components which need to be combined somehow or factored together. So for that, you have function simplify in MATLAB for any symbolic simplifications of algebra. So it will do all the simplifications automatically for you. You just write simplify on that expression with S, and then it will give you the simplest representation of that polynomial or rational function or whatever it is, okay, with some particular variables. Any questions on linear algebra part? Okay, linear systems. So let's say we're defining some state space system with given matrices A, B, C, D. All right. Now we want to find transfer function for it, like that. Okay, we want to convert it into transfer function. For that, you have a function which is called state space to transfer function, SS2TF. Okay, you put all these matrices inside that function, and you get numerator and denominator polynomials for your transfer function, which would be like that. Here, you see, these are coefficients of your numerator and denominator. Okay, 2 polynomials. If you want it to be in kind of algebraic form, you can also do that. Now, if you want, so this is a simplified function, okay? So we know the formula to find the actual transfer function, which will be C times Si minus A inverse plus times B plus D, right? That's standard formula that we are using all the time. So if you compute that, it will give you that kind of expression. Now, pay attention that these are exactly the same coefficients like here. So you have coefficient of 0 times S cubed plus 4 times S squared minus 1 times S. And here, further, you will see 3, okay? But same thing here. It's like 1 minus 7 minus 3. You have 1 minus 7 minus 3. Pay attention that this minus is coming from canceling these 2 minuses. You see, so this will be, if you kind of move in that minus here and multiplying all of the denominator equation by minus 1, then we'll get S cubed minus 7S squared minus 3S. So these are these coefficients. Okay, just because of the minus difference, then because of that, you have the difference between the coefficients. Clear so far? Okay. So now you want to go the other way around, from transfer function to state space, to convert it back. And as you know, you have many different ways to do that. You have canonical controller, canonical observer, diagonal. You have multiple different ways to convert it back because you have infinite number of representations for the same transfer function, for the same system. So what happens is that this one is giving you that companion form, which is classical controller form. And this is how it will look like. So as you can see, these are just negative coefficients of A1, A2, A3. This is the first row, okay, if you look in here. Second row, it will be 1, 0, 0, 0. So you have kind of main diagonal, everything else, it will be zeros. But below the main diagonal, if you remember in canonical form, you have ones on the below main diagonal. So that's exactly what you have here. Ones are below the main diagonal. The first row is minus coefficients of your poles, characteristic polynomial. Okay, B is 1 and zeros, and C is something else, which are coefficients practically of the numerator. Okay, So you'll have same coefficients here and here as well, like 4, -1, and 3. You get obviously exactly the same representation. So this is canonical controller form. How do you get canonical observer form? It's just very simple. It's just A transpose, P equals to C transpose, and C equals to B transpose. Right? So from these matrices that you computed, you can just tweak them a little bit and you get canonical observer form. Diagonal form you get from diagonalization. So you have the transform, which is transforming that to diagonal form. You can get diagonal form if you want. Okay, these are practically eigenvalues on the main diagonal, and the similarity transform, which are eigenvectors building that matrix of transform. Okay, so no issues here if you want to do that. For controllability and observability, we have also special functions. And these functions are CTRB for controllability matrix. So you're computing controllability matrix just by giving A and B, because this is all you need for controllability matrix. And then you can compute, for example, rank of that matrix. So this is how it will look like. So this is controllability. As you can see, this is vector B, AB, A squared B. Okay, you can actually compute it for the simple case. And this is invertible matrix, so the rank is 3, full rank. All right. Same thing with observability. The command is OBSV, observability, shortcut for the observability. And then rank of that matrix, I think also will be 3, right? Yes. So it's also observable system in that case. But for that, you're giving A and C matrices, because this is what you need for observability matrix computation, right? Not A and B. Now, any questions on that computation? Now, controller design. Let's say you, yes.
I do have a question. If you accidentally put in B, but like the dimensions are different, would it throw an error and like let you know?
Great question. Let's see. Let's try it. Say we have 1, 2. Let's pick simple example. And then you're saying that you are choosing here column vector, which would be, let's say, 1 and 2. Something like that, right? Arrow. So it helps you not to make that mistake. Throw cell. All right, so you have very convenient function which is called place. And place just putting poles wherever you want it. It's just placing the poles wherever you tell it to place it. All you need for that is just to find controller K. You just write in function place, function matrices A and B. All right, and where you want your poles to be. So it's vector, which should be obviously from the same dimension as one of the dimensions of the matrix A or vector B. Okay, so if this is 3 by 3, you need 3 locations. Okay, this is what you'll get. It will compute the vector K. That's it. This is as simple as that. So controller design in MATLAB is just one line. You say in place wherever you want it. It will place it wherever you want it. Okay. Any questions on controller design in MATLAB? And by the way, this is a very important function because help for that function, if you go to MATLAB help and you search for place function, it will give you many, many important examples that I want you actually to look through, because it gives you how to simulate systems, how to get step responses, how to get combinations of different inputs and outputs, how you control that in closed loop, how you simulate that in closed loop. It gives you a lot of information and a lot of examples on how to use that state space approach in MATLAB, okay? If you do not want to use Simulink for all these blocks and putting them in loops, you can do all of that in MATLAB, including your project, okay? If you don't want to use Simulink, you don't have to really. You can simulate almost everything in MATLAB without Simulink. It's code. And code is not that difficult, okay? You have just LSIM function, you have step function, you have all kinds of things that you will need for that type of project. Okay, so you can do that in MATLAB, in pure MATLAB without simulating. All right, just to validate that we get whatever we want roots of characteristic polynomial of A minus BK matrix. These are our closed loop poles. And we want them wherever we said they need to be, which is these numbers. These are exactly these numbers in different order, but same numbers. Okay, so we got them wherever we wanted them. Okay, observer design, same function. If you remember, these are dual problems, which means the only difference that you need to use A transpose and C transpose instead of B. All right, everything else is the same. And then at the end, you need to transpose all of that because L is column vector, not row vector. Okay, and this place matrix will be row vector, not column vector. So here you have a lot of transposes to do. Okay, actually 3 of them. So you're transposing A matrix, you're transposing C matrix, then you're saying where you want the poles to be, and then you're transposing the result to get that vector L, which is column vector. Practically done. So I designed observer with poles at minus 10, 11, and 12. Now, tricky question. Well, you can validate that. Obviously, you get A minus LC matrix instead of A minus BK matrix. So characteristic polynomial and roots of the characteristic polynomial will be in the places where we hope them to be. Okay, system is observable, no problems, no issues. But now we want observer poles at negative 10, all of them, or controller poles, all at the same place. And I'm trying that function, and this is what I get. What happens? You see error. Like instead of like 10, 11, and 12, I decided on 10, 10, and 10. Why not? I mean, it's observable. I can put them anywhere I want. But it screams at me, says error. So it's interesting that MATLAB implementation is not allowing you to use same location for the poles with the function place, which is very interesting thing. That this place function is using such algorithm, which is not allowing you to put all of them in the same place, which is kind of limitation, which could be avoided. And how would you avoid that problem? You have multiple ways to avoid that problem. First of all, you decide where your poles are, right, in the first place. So why not to put them at, like you want them all to be close to 10, so put them 10.01, 10, and 9.99. This will work, okay? This is one possible way of like, putting them almost 10, but not exactly 10, because it needs to be different, all right? But you also have Ackermann formula, and interestingly enough, this formula was deprecated in MATLAB probably like 15 years ago. It is still available. You can still use it if you have controls toolbox, but you will not even find that in help. And the function is called Acker. And Acker doesn't care if you put it at the same place. You still can place them at negative 10. Again, the syntax is exactly the same syntax like place, just different function, Acker. It's sitting somewhere hidden in the code of MATLAB. Like people who know that function, they use it. People who don't know, they just don't know what to look for because they will not find it in help really. Only probably like 15 or 20 years ago, they still have it, deprecated function. But this function gives you actual answer. So let me comment that things that it will run actually. And then you get your L, okay, with that function. So this works. Okay, last thing, the textbook that we are using from time to time has codes which are solving all of the questions in the book using MATLAB, including numerical computations, including symbolic computations. This code is available on the textbook web page. You can download that zip file, and it's like divided by chapter. All of the questions are solved, and before you start working on your project, I strongly recommend just going through this code, trying to understand what it does. It's not very long, okay? Not too much code. Very short snippets of code like this one, okay? This will prepare you to read these codes, okay, which are in the textbook. If you have any questions, issues, anything, shoot me email, and we'll figure out how you can learn all of the missing parts of the MATLAB if you need it. Because there are some symbolic computations. You don't really need the initial chapters computations, which are integrals and other things, like numerical integrals. If you remember, we had a lot of that stuff in the initial first lectures. So you don't have to go through all of this numerical or symbolic integral computations. Like start to concentrate from probably like chapter 2.5, 3, where we start to design controllers and that kind of things, or converting transfer functions to state space, that kind of things. Okay, so this is what you actually will need. Any questions? All right, thank you.